should actually record that. Many events can't be predicted with total certainty. The best way we can say it is how likely it is to happen using our probability. Now, if you remember your probability, and we'll get to the other side, it was, what are my successes over all the possible outcomes? So if I want to roll a 2 on a set of dice, the probability was there's only 1 2 on a regular die over 6 possible outcomes. But we're going to apply this to first females in the class with brown eyes. So in any class, there are females and males who have blue, brown, and green eyes, or something close to it. Create a table that shows all possible combinations of genders with those eye colors. This is going to be known as sample space. So in fact, we're actually going to set kind of what's a two-way frequency chart. We're going to make it look just a little bit different in the fact that we're going to make it more of a simple chart. Actually, let's make this a little bit higher. Let's do something like that. Where on the side, I'm going to list male and female. On the top, I'm going to list my 3 eye colors. We'll go blue. We'll go brown. We'll go green. And just for the sake that it happens, let's put other. Let's do a quick poll. If you don't know your eye color, guess at it, I guess. Or ask someone what your eye color is. How many guys in here think they have blue eyes? Raise your hand if you think you have blue eyes.
Oh. Okay.
So we have 0 with blue eyes, is what I'm saying. How many of you think you have brown eyes? Guys. Sorry. 1, 2, 3, 4. We can use you. 5. We'll go with 5. How many think you have green eyes? What color you got?
Turquoise. It's in between. It's green, blue.
Okay, then we'll go other. So we have no greens. And we have a green, blue. We'll go other. That's fine. All right, for girls, how many of you think you have blue eyes? 1. I think we're a heavy brown class. How many people think you have brown eyes? 1, 2, 3, 4. How many got green eyes? Madison. How many is an other? No one's an other? All right, we're good. So how many guys do we have in the class? If we're doing this two-way frequency chart, how many guys are in the class? 6. Do we actually have 6? Let's double check. 1, 2, 3, 4, 5, 6. Cool. How many girls do we have in the class? 6. Do we actually have 6? 1, 2, 3, 4, 5, 6. Hey, the math works out. How many total blue-eyed people do we have? 1. How many brown-eyed? 9. How many green-eyed? 1. How many other? 1. How many total people are in the class? 12. So that's our total. That's our total people. Total peeps. All right, so then we talk about the probability that someone's a male. How many males do we have in the class? 6. So the probability is going to be 6 over... How many total people are in the class? 12. All right, so it's 6 over 12. Now, note how this is set up. This P male says, what's the probability of being a male in the class? That's what this is a whole sentence. What's the probability of a male being in this class? There are 6 males over 12 total. I guess we could simplify that to 1/2. That seems a little easier. It's kind of a 50-50 shot. If I put you all in, maybe I should put your names in a hat, not all of you in a hat, and I pull out a name, we got a 50-50 shot of it being a guy. Blue eyes. Who wants to take a shot at what's the probability of having blue eyes? Josh.
12.
What was that? 1/12. Perfect. We have one person that's got blue eyes out of 12 people. We can't simplify that. Probability of male is 1/2. What's the probability of being female? Probably 1/2. We don't have to look at it. It should be 6/12, but we're going to go straight to 1/2. Let's go over brown eyes. What's the chance of, I put all your eyeballs in, no. I put your names and I put brown eye next to it. What's the chance that I pick someone that's got brown eyes? What is that probability? Who's got that? Justin. 3/4. So you probably did 9/12, which reduces down to 3/4. Cool. What's the probability that someone has an other eye color? What's the chance I pick Isaac, I guess? Yeah. 1/12. That's why I put the column in there. What's the probability I have green eyes? I got this one. There's one green out of 12. All right, those are all our probabilities of just kind of simple things. Now we're going to talk about finding each of the following probabilities. We're going to add the word or to it. So the first one we're going to pick is the probability we have a male or a female. What's the probability that I put all your names in a bag and I pick out a male or a female name? 12/12. That is 1. In fact, I put a little note to myself that when we talk about this, that is all possible outcomes. This one right here is all possible outcomes. And what I also want to put on here is when you use the word or, you can actually break apart the probability. You can come up with, we can rewrite this as the probability that it's a male plus the probability that it's a female. And if we have room, I think I got room, we can actually go further and say, okay, the probability of picking, what's the probability of picking a man in this class? 6/12 or 1/2. What's the probability of picking a female? 1/2. Guess what 1/2 plus 1/2 is? 2. Well, 2/2, not 2 halves. Well, I guess 2 halves. I guess that's fair enough. It's fair enough. You're not wrong. I was looking for a 1, though. If you have 2 halves of pizza, you have a whole pizza, right? All right. What's the probability of having a blue or brown eye? Now, once again, if we can't just count it up and we already have probabilities, we can do probability of blue plus probability that it's brown. I think I'm going to write this one down below. I do want to add something to the right there. What's the probability that someone has blue eyes? What did we say? 1/12. What's the probability that we have someone with brown eyes? 3/4. I'm going to use the 9/12 though, because we have to add those together. So it's never a bad idea to just go back, because we know when we add, we have to have a common denominator. So that is 9 plus 1, which would equal 10/12, which we could then simplify to 5/6. Does that match? If I look at the chart, are there 10 people that have blue or brown eyes? Okay, so it's 10/12. So that math works. I also want to point to something with that blue or brown. This is something called mutually exclusive. And we'll talk about this a little bit on the other side as well. Mutually exclusive. My thing would write mutually exclusive. Mutually exclusive says that they both can't occur at the same time. Although, could someone have 2 different eye colors?
Yeah.
So in our class, this is mutually exclusive. If we had someone in here that had a brown and blue eyes, that would no longer be mutually exclusive. That would be called mutually inclusive. Because there would be a person that fits both categories. So if there's no overlap, it's known as mutually exclusive. Either you're blue or you're brown. If it's not, then it's mutually inclusive. So once again, mutually exclusive is if you're either one or the other. You can't have your foot in both camps. Does that kind of make sense? Okay, so mutually exclusive if you can't have a foot in both camps. So blue and brown eyes. Oh, we just did that one. I think I wanted to eliminate that one. Oh no, I have female and brown eyes. We're
and.
good. Oh, there we are. I'm zoomed in the wrong place. Yeah, it is and. So what's the probability you have blue and brown eyes in this class? So think of the word and. You have to have both. Yeah. 0. We have no one in the class that's both blue and brown eyes. Our next one says find each of the probabilities. Now we're going to do male or blue eyes. Are those mutually exclusive? Ben, you're saying no. Why is it not mutually exclusive?
Because you can be a male and have blue eyes.
Because you can be a male and have blue eyes. Those are not mutually exclusive. So those are going to be mutually inclusive. So this one's going to be mutually inclusive. I'm just going to put inclusive right now. That is inclusive. There are men that could have blue eyes. So when you're doing probability with inclusive, you always run the risk of double counting. So when you're doing the probability of inclusive, it's going to be the probability that you are a male plus the probability that you have blue eyes. But let's say you had a male with blue eyes. You just double counted them. You counted them as being a male, and you counted them having blue eyes. So when it's inclusive, you have to think about subtracting any overlap. That would be a male with blue eyes. All right, what's the probability of being a male in this class? Let's do the over 12s. Just shout it out. What's the probability of being a male in this class? 6 over 12. What's the probability of having blue eyes in this class? 1 over 12. Are there any males with blue eyes? No. So there's no overlap, so we're subtracting 0 over 12, which is like we're subtracting 0. So our total is going to be 7 over 12. Once again, if we had a male in here with blue eyes, I'd have to subtract it because I counted it twice. I would have counted it here, I would have counted it here, so I have to subtract one of them. Otherwise, you can end up with more than 100% chance of picking something. All right, what's the probability of its female and brown eyes? So once again, it's inclusive. So that way we have to think about what's the probability of being a female. I'm just going to put an F just to save time. Plus the probability that we have brown eyes. And then we're going to subtract any overlap. That's the probability it's female with brown eyes. All right, probability of being a female. That's 6 over 12.
Isn't it and those? Would there be some?
Oh, I'm sorry. I didn't realize it was and. It is and. I wanted it to be or. We're good. No, let's leave it as and. Let's leave it as and. I think I wanted another or in there, but that's okay. Let's leave it the way it's written. Okay, so if it's and, we're not actually going to do any of that. Because we just have to go up there, and we actually have to count those. So female and brown eyes. How many females have brown eyes in this class? How many? 4. Out of the 12 people that are in this class. So you have a 1/3 chance of being a female and have brown eyes. All right, the very last thing we're going to talk about are not. The word not. Not is known as a complement. These are complements. The probability of not blue eyes. So the probability of not blue eyes. So these two things are known as complements. So what we could do is, we already know the probability of having blue eyes, right? We've already calculated what's the probability of having blue eyes. What's the probability of having blue eyes in this class? 1 in 12. What would the opposite, so not blue eyes, be then? Charlie?
11.
It'd be 11 over 12. So notice complements are kind of like opposites of each other. If one is 1 over 12, the other one's 11 over 12. So we can oftentimes use complements if I already know it. If I already know how many people have blue eyes, I just flip it, and I have now 11 over 12. So if I want to find the probability that it's not male, and I already have the probability it's male, well, this one isn't so good because that's 6 over 12. Kind of the opposite of 6 over 12 is 6 over 12. Okay, let's put some formal stuff to that stuff we talked about. All right, simple probability. Now, first of all, for simple probability, we can write them as fractions, decimals, or percents. A lot of times we leave them as just fractions, all right, unless it specifically says I want it in percents. A lot of times we just leave it in fractions because they're as good as any, and I don't have to worry about having a calculator on me. So when we're doing simple probability, that is the probability that one event happens, just one event, that you are a girl with brown hair, or brown eyes, sorry. If that's the case, we're just going to do the number of ways it can occur. There's 4 of you in here that have brown eyes. Out of the total number of possible outcomes, there's 12 people in here. So 4 out of 12 is our success over a failure. Now, like I said on the other side, mutually exclusive events. Mutually exclusive events are those that can't happen at the same time. They can't happen at the same time. These are events that can't happen at the same time. So when we talked about eye color in this class, you couldn't, in this class, have brown and blue eyes at the same time. However, you could be a girl with brown eyes. So those would not be mutually exclusive. So if I said you want to be a girl and have brown eyes, those are not mutually exclusive. Those are inclusive. All right, then the last thing we're going to talk about today are theoretical versus experimental probability. Theoretical versus experimental probability. So theoretical probability is the probability that is determined on the basis of reasoning. So example, what is the probability of rolling a sum of 4 with a pair of dice? So we have a pair of dice that we're going to roll. These are all of our possible outcomes. How many outcomes is that? 36. There's 36 of them. There's 36 of them. And then if we look at for things that add to 12, I don't really have a good color that will show up in here, maybe purple. So look at the places that add to 12 or 4. We have 1 and 3. We have 2 and 2. We have 3 and 1. Is that a coincidence that they make a diagonal? No. Check any one of the diagonals. This is 9, 9, 9, 9. So our diagonals will actually give us our sums. It makes it a little easier if it's all written out. So that means, what is our probability of getting a sum of 4 with 2 die? What is that probability? So let's put that down. Probability sum of 4. What is that probability? 3 out of 36. Which we could reduce down to 1 over 12. I heard Isaac say that earlier. That is our definite probability of getting our sum of 4. Well, if I had a 100% chance of getting a 1 in 12 chance, that means if I roll 12 die, or if I roll this 12 times, am I guaranteed to get a sum of 4?
No.
No. If it was, it'd make betting a lot easier, wouldn't it? If it was always the probability was correct. So the next thing we talk about is experimental probability. The actual result of an experiment which may be different from the theoretical probability. I'm going to change these numbers. I'm going to make them 10 because we're actually going to do this. We're going to do 10, 100, and we are going to do 1,000. Barring any time. Now, we are not going to take out 2 die and we're not going to roll them 1,000 times. We're going to cheat. We're going to use a website that's going to do it for us. Yeah. Let's see if I can bring that up without closing that down. Cool. I think I got the website up. Let me grab my mouse with me. Charlie broke his pencil. Oh, no, we closed it. I think so. Roll the die got net. Let's go ahead and set this up. So we're going to roll the first one 10 times. We're going to do 2 die. Let me grab my iPad real quick. So we are going to roll a die.
Look at it.
What are we looking at?
The mouse
Is it shaking? Is it on the move? Oh, it's on the move. It's on the move. All right. So we're going to roll 2 die, 6-sided. We're going to do it 10 times. Real quick, I'm going to change. Oh. All right. I rolled it 10 times. Now we're looking out for 4s. Did we get any 4s? No. So according to my experimental, when I rolled 10 times, what is the probability of getting a 4? According to our experiment. We rolled 10 times and how many worked? 0. So our probability of a sum of 4 is 0 over 10. Well, that's no good. So that's experimental. Let's roll it 100 times. Let's go there. Let's make sure we're up at the top. All right, so count with me. Can you see it kind of scrolling? All right. Are we going to get any? 1, 2, 3, 4, 5, 6.
7. 8. 9.
Oh, I missed it. 9. 10. All right, we got 10 of them. We got 10 of them. So what's the probability of getting that? That would be 10 over 100, which actually equals 1 over 10. What was our theoretical probability? 1 over 12. That's closer than 0 over 10, right?
Yeah.
All right, what do you think is going to happen if we roll it 1,000 times? You think it's going to be closer? Let's check it out. Oof. Get ready. Get ready. I'm going to scroll up. Are we ready? It's a big one. All right, I need help on this.
1. 2.
Did you see 2?
I think so.
Oh, yes.
No, I didn't. No.
Okay.
2, 3.
It's 3. That's 3? Yeah.
4.
4,
Wait, what?
5, 6.
6.
Josh is 1. 7.
7.
8. 9.
Wait. No.
No? Okay.
Nine.
Or no.
10.
10.
11.
11.
12.
12.
13. 14.
15. Did we max one?
Did we? I'll go up. I didn't see one.
Do you think if you hit Control F and put 4, would it show all of them?
Maybe. What do we get?
Yes, I think it would work.
15.
Should we
But
do
then
that?
I think you need to make sure there be no other 4s anywhere else.
16.
Well, it's kind of like me.
17.
Close enough.
Yeah.
18. You're missing some.
19.
19.
Hypothetically.
20.
And then you can-
21. 22.
23. 24.
4.
So we're like 8 of the way.
Did we see a 25?
No.
I didn't see one.
24. I think so.
I see a 25,
Yeah.
26.
26,
27.
27.
28.
28.
Where?
27.
I think we're still at 27.
27.
I thought you like last.
Your eyes are deceiving.
8. No, that's a 6.
You're getting old.
I cannot see.
We should just like
28.
8.
28.
No.
9.
9.
Yeah.
20, 30.
30.
41.
31,
I thought, yeah, I saw the 3 and I was like,
That's all one.
very fast.
31, 32.
3.
Am I at 32?
That's
Yeah.
33.
Yeah.
3.
33?
Yeah.
Yeah, yeah.
Okay, 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 okay.
34.
34, 35, 36,
7.
8, 9, 10, 11, 12. Oh, what are we on?
40. 41.
41,
41.
I'll
42,
Come on, Josh.
3.
43, you said?
Yeah.
Yeah.
40.
They're just black.
4.
They're just black circles.
Look at the numbers. 45,
Me either.
46,
Numbers in here.
47,
40.
48.
8. 9. 10.
10. So we're at 50?
40.
I saw snake eyes.
51.
52, 53. I need help. 54. Don't die on me. We're getting there.
We're like halfway.
55.
5.
Can we just play you pick up?
56.
57,
58.
88,
9.
59,
Man, it's too early in the morning, dude.
6.
60,
7.
No. Oh, no, it's not. It's not.
Josh, what's your name?
61. Am I right? Are we on 61? Focus.
Yeah.
I'll have to go back.
62.
62,
Yeah, maybe we should double check.
63. Are we 64 or 63? 63. Thank you, Kirsten.
64.
Now we're 64, 65, 66, 67,
If we get 100 on the dot.
67 or 68.
8. It would be 8.
Yeah.
What?
9,
70.
70, 71, 72. Oh, 71, 72,
These are just showing up at black.
73, 74,
Same. I've been doing that.
75,
I thought it was just lagging.
76.
76,
My brain is the one that's
77,
7, 78,
8,
79, 9, 4,
80,
80,
81,
82,
82, 83,
84,
4,
84, 85, 86, 87, 88, 89,
90. You just passed one, didn't you? Yeah, I think so.
I don't see one,
No.
90, 91, 92, 93, 94, 95, 96,
Oh, then go over. 97.
97, 98, is that 98?
Yeah, it is 8.
Oh no.
It's supposed to be 1 at 12.
Yeah, but
9.
Or 100 out of
100, 101, 102,
Oh, well.
103.
Oh, I can't remember that.
104.
4.
We're so close. 105. That's it.
Oh, 105.
Now we have to go back and check them.
Just do control F.
Yeah.
Why control F?
Yeah.
Because then it shows
Go
up
back
on
and
the
do
board.
control F and then
It highlights them.
Oh, I got you. So I could hit find.
Yeah.
Oh, that would be a good idea. What did we had? We had 104,
Yeah.
105. It was
105.
Let's just recount
It was
them.
five.
No, we could just do the control find thing now.
Oh, well, we'll try it.
Can we try?
105 out of 1,000. What does that reduce to? So while I'm doing this, let's reduce it.
Justin.
Go Big J.
What, it'd be like,
And
it'd
then
be
put a
like
4.
21 over 200 now.
Oh, remove any other 4s that aren't actually.
It's not highlighted.
Well, there's 1,
There's 2.
2.
2.
Oh.
I don't think it highlights.
No, it says it in the top.
What top?
The one that's
3,
not highlighted.
4. So it's saying there's 106 of them.
Saying there's 106 again.
So we must have
Yeah,
missed one.
So you.
It is highlighting them.
So then how does it like, so we were 1 off.
Yeah, that's good enough. Let's leave 105
It's even.
because we counted that.
Yeah.
Let's do that.
Hey, but now you know you can do this for the rest of the classes instead of doing
Isn't it? Or
Yeah.
even-
Well, we're still gonna count
Oh,
it.
you got it.
All right, guys. So we have what? 105 out of 1,000. What does that reduce to?
21 over 200.
Say that again.
21 over 200.
21 over 200.
Yeah.
What is the decimal behind that?
.105.
0.105. What was our theoretical probability?
1
1 over 12.
It was 1 over 12. What's 1 divided by 12 in decimals?
8 point, oh,
0.083 repeating.
0.83.
We learned this.
0.083
You okay? You weren't here.
repeating.
All right.
Not that.
Are we getting closer though? Versus 0,
Yeah.
and then
It's 0.083 repeating.
That's what he did.
0.0.
Yeah,
We're fine.
Yeah, okay.
We're fine. We're fine. So we should get closer. If I did it, so we're gonna do 10,000 next, okay?
What?
So we're gonna count 10,000 of
Yeah,
them.
we can just use that.
Oh, we can use the cheat thing.
Yeah.
Yeah. Let me bring this back up.
Well, I'm sorry.
So we got 105 out of 1,000, which we said, what was that in decimal form?
0.10.
Okay, let's try.
Our brains are fried.
Well, we're not going to count this time. We're going to use the control F4. Let's do it 10,000 times.
I'm gonna just subtract 4, I think.
Yeah, you.
Yep.
backspace because otherwise it won't register if I put it in again.
I got 882. It's right up there. So we subtract 4 of them. 878 out of 10,000. What is that in decimals?
Big J.
I gotta use my calculations and things.
0.878.
Say that again.
That's close.
0.0. Say that one more time.
0.087.
0.87. Are we a lot closer?
Oh, that rounds up to an 8.8. Rounds up to an
88. What would happen, do you think, if we did 100,000?
8.8.
Closer.
What if we did 200,000? Even closer. That is something called the law of large numbers. That is something called the law of large numbers. The more times you do something, the more likely it's going to be closer to your theoretical probability. It's not guaranteed. It's just most of the time, the more times we do it, the closer we're going to get. That is called the law of large numbers. All right, the very last thing we're going to do today in theoretical probability is we're going to read a histogram that is not done correctly. What is wrong with this histogram? Josh.
Instead of there being like one number at the tick line, it's like there's dash numbers.
There's dash numbers. So if I was to correct this, I would just go, oh, that's 10. This would be 20. This would be 30. This would be 40. And this would be 50. So we corrected their mistake, but we can go ahead and go, how many games did they play? Based upon this chart, how many games did they play?
I got 16.
You got 16? Who else got 16?
Oh, I got it.
It is 16. It's 16. What is the probability of scoring 11 points? Who wants to help me come up with that probability? What's the probability of scoring 11 points based upon this chart? Now, we don't know exactly 11. We just have a group. Josh,
1/4.
you're saying 1/4. How'd you start that? You get 4 over 16 probably,
Yeah.
which equals 1/4. I guess I should have probably started off with probability of 11 equals 4 over 16, 1/4. Would that be considered experimental or theoretical? If we played the games. Yeah,
Experimental?
it is experimental.
Oh, yeah.
That is experimental. I'm basing it upon games that were played. I didn't go through every position and figured out, I didn't play Madden football and came up with the calculation of who's going to win. This is experimental. I played 16 games. Based upon my experiment, we have a 1/4 chance of scoring 11 points in our next game. All right. Any questions on what we just learned today?